What is the unit and formula of surface intensity? Whether you need good help, a genius writer, a brainy tutor, or a data wizard, Intuito4U has them all. It's like having a research dream team on demand.
Have you ever tried to describe how bright something is? You say it's super bright or really intense. Well, it turns out that in the world of science, those words are a total minefield. Yeah, measuring light is way more complicated than it sounds. So let's get into it. So let's just start with this question. When a scientist, like a physicist, uses the word intensity, what are they actually talking about? You'd think there's one simple answer, right? Well, that's where all the trouble begins. Take a look at this. In your average physics class, intensity is just power spread over an area. Simple enough. But in radiometry, that's the science of measuring light, it's power shot out in a specific direction. And for sound, it's something different again. This isn't just about splitting hairs. It's a clue that we're dealing with a much bigger, more fundamental issue. And that brings us right to the heart of the matter, this constant battle between two different worlds, the world of pure physics and the world of human perception. Okay, so here's the bottom line. The whole reason this is so confusing is that there are two completely different ways to measure light. We can measure it like a machine would, just counting up every last bit of raw physical energy. Or we can measure it based on how it actually looks to us, which is a totally biological and subjective experience. And this slide just nails the two sides of the story. On the one hand, you've got the human eye, this incredible, but let's be honest, kind of biased biological tool. And on the other, you have a perfect physical sensor, a totally objective machine that just measures all the energy that hits it, period. These two very different detectors give us two completely separate systems for measuring light. So let's start with the machine's point of view. This is the world of pure objective physics, and it has a name, radiometry. Radiometry is all about measuring electromagnetic radiation based on its raw, unfiltered power. A great way to think about it is like a rain gauge. It doesn't care if the rain is clean or dirty, or if it came from a big cloud or a small one. It just counts every single drop that falls into it. Radiometry does the same thing with light energy. It's a totally unbiased count. And the scope of radiometry is huge. It's not just concerned with that tiny little rainbow of light that we can see. As you can see from the spectrum, it measures everything, from radio waves all the way up to gamma rays. To a radiometer, it's all just energy that needs to be counted. So in this system, the language is pretty direct. The total power shooting out of a light source, we call that radiant flux, and it's measured in watts. Yep, the same watts you see on your electricity bill. And the amount of that power that actually lands on a surface is called irradiance, which is just watts per square meter. See? It's all about raw energy. But now, here comes the plot twist, the biological wildcard that changes the entire game, the amazing and very particular filter of the human eye. You see, unlike that perfect impartial sensor, our eyes are, well, they're picky. They're full of these little light catchers called rods and cones. And as you can see from these curves, they totally play favorites. Each type of cone has a specific color that it gets way more excited about than any other. And when you put all that together, the result is pretty wild. Let's say you have 1 watt of pure green light and 1 watt of pure blue light. Physically, they have the exact same amount of energy. But to your eye, that green light is going to seem way, way brighter. Our vision is just massively biased towards the middle of the spectrum. And scientists, being scientists, have mapped this bias perfectly. This beautiful curve is called the luminous efficiency function, and it's basically this secret recipe for human vision. It shows us exactly how our eyes weigh the brightness of different colors. And see that peak right there at 555 nanometers? That's the green-yellow sweet spot that we are most sensitive to. This curve is the Rosetta Stone that lets us translate objective physics into subjective human sight. So how do you build a whole system of measurement around this very human filter? Well, that brings us to our second science, one built just for us, photometry. Photometry is the science of measuring light the way we actually see it. So, if radiometry was that rain gauge counting every single drop, photometry is like measuring how much that rain actually helps your garden grow. A nice gentle shower is way more useful than a massive downpour that just washes everything away, right? Photometry weights the raw energy using that luminous efficiency curve we just saw. And you can see here how the two systems line up perfectly. It's like a parallel universe. Every single radiometric idea has a photometric twin. The raw power of radiant flux in watts becomes the perceived brightness of luminous flux in lumens. The raw energy hitting a surface, irradiance, becomes the perceived brightness on that surface, illuminance. It's the same basic idea, just seen through two very different lenses. Okay, so how do we actually cross over from the physics world to the perception world? It all comes down to this number, 683. At our eye's absolute peak sensitivity, that 555 nanometer green light, 1 watt of physical power is defined as having a perceived brightness of exactly 683 lumens. That's our magic conversion factor, but only at maximum efficiency. For any other color, 1 watt of power will give you fewer and fewer lumens, based on how far you are from that green sweet spot. All right, that was a lot of theory. Let's bring this all back down to earth and see how it shows up in your everyday life. Here's a perfect one. Have you noticed we don't really buy light bulbs based on watts anymore? Now it's all about lumens. Why is that?
Well, it's simple. Watts only tell you how much electricity the bulb is sucking from the wall. That's a radiometric measure. It's about energy consumption. But lumens, that's a photometric unit. Tell you what you actually care about. How bright is this thing? Gonna look in my room? A super efficient LED can give you a ton of lumens with just a few watts, and that's exactly what you want.
And what about lux? This is how we measure the perceived brightness of a room or an environment. And the scale is wild. Direct sunlight can be a blinding 100,000 lux. A nice, comfortable office is maybe around 500 lux. And then you get down to a full moon, which gives off just a tiny 1/10 of 1 lux. It's a really useful way to talk about how bright a space feels. And where does all this lead? To some really incredible science, like color. This beautiful shape here is the famous CIE chromaticity diagram. It is, literally, a map of every single color the average human eye is capable of seeing. It was built using all these principles of photometry, and it's the foundation for your TV screen, your computer monitor, everything. So if there is one big idea to take away from all of this, it's this right here. We tend to think of scientific measurement as this cold, objective thing. But when you're measuring something we perceive, like light, sometimes the most useful and most powerful measurements are the ones that are custom-built for the observer, for us. And that kind of leaves us with one last big question to chew on. We've just seen how our own biology completely reshapes how we measure something as fundamental as light. So it makes you wonder, what else out there in our science and our understanding of the universe isn't defined by some objective reality, but is actually defined by us and the unique way we perceive the world?
And subscribe now for amazing videos just like that. Thanks for watching.